Let us illustrate the way how to solve the system of linear autonomous ordinary differential equations by the following example. X derivative is equal to x plus 2y and y derivative is 2x minus 2y. So first we write the matrix A, 1, 2, 2, minus 2. This is the matrix of the coefficients at x and y. Then we want to find the eigenvalues and eigenvectors. We compute the determinant of the matrix, which is minus 2, minus 4, which is minus 6. We compute the trace of the matrix, which is 1, minus 2, which is minus 1. And we can build a characteristic equation, which is lambda square minus trace times lambda plus determinant, which is equal to 0. Let me explain this computation in more detail, why the characteristic equation is exactly in this way. If we have a matrix, say A, B, C, D, and we want to find a vector B, which is such that AV is parallel to V, that means AB is some number lambda times V. So we subtract lambda V and we have AV minus lambda V is 0. And we want to factor out V, but before we add the identity matrix E, where E is 1, 0, 0, 1. Now we can factor out V and we have A minus lambda E times the vector V is 0. This is a matrix, this is a vector, and we want this product to be 0. This is always true when V is 0, but we are interested in some non-zero vector. And then this system has a non-zero solution if and only if the determinant of this matrix is equal to 0. Determinant of A minus lambda E is 0. And this is the characteristic equation which we have here. It is a polynomial of order n for an n by n matrix in the unknown lambda. And the way from here to here is very simple. If we go back to A being ABCD minus lambda 1, 0, 0, 1, this means ABCD minus lambda 0, 0, lambda, which is A minus lambda, B, C, D minus lambda. And we want the determinant of this matrix. So the determinant of A minus lambda E is A minus lambda, B, C, D minus lambda, which is A minus lambda times D minus lambda minus BC, which is lambda square minus A plus D lambda plus AD minus BC. And we want this to be equal to 0. If we compare this equation with lambda minus lambda 1 times lambda minus lambda 2 is 0, where lambda is the unknown and lambda 1, lambda 2 are the two roots, then if we expand this multiplication, we have lambda square minus lambda 1 plus lambda 2 times lambda plus lambda 1 times lambda 2. Now, if we compare these two results, then we see that sum of the roots is equal to sum of the elements on the main diagonal, which is called trace. And the absolute term is the product of the roots, which is the determinant. So this comparison shows that the trace of the matrix, the sum of the elements on the main diagonal, is equal to the sum of the eigenvalues, and the determinant of the matrix, which is for 2 by 2 matrix AD minus BC, is equal to the product of the eigenvalues. This is true even for larger matrices. Then the trace is again the sum of the entries on the main diagonal, but the determinant is a more complicated expression for larger matrices. So this is the explanation how we can quickly write down the characteristic equation just using these two very simple steps, very simple computations. Now this is easy to solve, and we see that lambda 1 and lambda 2 is 2 and minus 3. The product is minus 6, which is the determinant, and the sum is minus 1, which is the trace, which is the trace of the matrix is the sum of the eigenvalues. And now for each eigenvalue, lambda 1 and then lambda 2, we go back to this equation, because now this bracket is already a known matrix and we can solve for the vector b. So first, for lambda 1 is 2. We build the matrix A minus lambda 1e, which is the matrix A, and we subtract 2 from the entries on the main diagonal. 1 minus 2 is minus 1, 2 is unchanged, 2 is unchanged, and minus 2 is minus 4. This matrix must be singular, the determinant must be 0. Is it so? Yeah, the second row is minus 2 times the first row. It is good. And now we want to find a vector such that when we multiply this matrix by the vector, we get 0. Actually, we want to find a canon, the null space in this matrix. Or if you look at the rows as vectors, we want to find a vector that is perpendicular to this row. And for a 2 by 2 matrix, 2 by 2 vector, to find a perpendicular vector, we just swap the two components and we multiply one of them with minus 1. So if we change these two and multiply minus 1 by minus 1, we get 2, 1. And similarly, for lambda 2 is minus 3, we build the matrix A minus lambda 2e. Now we subtract 3, that means we subtract minus 3, that means we add 3 to the entries on the main diagonal. So 1 plus 3 is 4, 2 is unchanged, and minus 2 plus 3 is 1. And again we see that say the first column is 2 times the second column. And then we can easily find the second eigenvector corresponding to the second eigenvalue by, say, considering the second row, swapping the two entries into 1, 2, and multiplying one of them with minus 1, say 1 minus 2. It is easy to check that these vectors are indeed eigenvectors for this matrix, if we multiply this vector with the matrix A, we should get the lambda 1 multiple of the same matrix. So a quick check, which is not a necessary part of the computation. This is just for us to be sure that no errors are on the way. If we compute A times V1, which is 1, 2, 2, minus 2 times 2, 1, then we have 2 plus 2 is 4, 4 minus 2 is 2, which is indeed 2 times the eigenvector itself. So you see, this vector 2, 1 is special in the sense that if you take the vector and multiply by the matrix, you get the same result as if you take the vector and multiply by a number 2. And similarly, we can quickly check that V2 is correct if we multiply V2 with the matrix A from the left. So we have the matrix 1, 2, 2 minus 2 times 1 minus 2, which is 1, minus 4, which is minus 3, 2, plus 4 is 6, and this is indeed minus 3 times this vector itself. Minus 3 plus 6, yes. So once again, you see this vector 1 minus 2 has the property that if you multiply the vector by this matrix, or if you multiply the same vector by the number minus 3, you get the same result. And this is exactly the definition of an eigenvector, together with the condition that eigenvector must be non-zero, which is true. Well, and having V1, we can build the solution, namely E2 lambda 1t V1. Having V2, we can build the solution E2 lambda 2t V2. We can multiply any solution with any constant, and we can add these two solutions, and this is the general solution to the system of differential equations. Which in our case means C1 E2 2t times the vector 2, 1 plus C2 E2 minus 3t times the vector 1 minus 2. And if you want the x and y components, then x is the first component and y is the second component. So we copy the scalar coefficients C1 e to 2t times 2 plus C2 e to minus 3t, and the second component, the function y, is C1 e to 2t minus 2 C2 e to minus 3t. Well, this is the general solution containing two integration constants, C1 and C2. If we are given an initial condition say we want x at 0 be 7 and y at 0 be minus 4. If we are given this extra information, if we are given these extra equations, Then we can find the values for the integration constants C1 and C2 such that these two functions satisfy not only the two differential equations, but also these two initial conditions. This value 0 for t is very nice, because then e to 0 is 1, right? This is a very nice value to work with. So we have, if we substitute 0 for t, 7 for x, and minus 4 for y, we get two equations for two unknowns, C1 and C2, which in this case will be 2C1 plus C2 is x, which is 7, and C1 minus 2C2 is y, which is minus 4. Well, this can be solved by various methods. So, say we want to get rid of C2, and this can be achieved by taking 2 times the first plus the second. And then 2C2 minus 2C2 disappears, and we have 2 times 2 is 4, plus 1 is 5C1. And on the right we have 2 times 7 is 14, minus 4 is 10. That means C1 is 2. And when we have C1, we can express C2, say from the first equation, because then 2C1 is 4, and C2 is 7 minus 4, which is 3. And when we have the values for the integration constants, we can find a particular solution. Namely, x is C1, which is 2 times 2 is 4 e to 2t, plus 3 e to minus 3t, and y is C1, which is 2 e to 2t, minus 2c2, which is 6 e to minus 3t. So this is the particular solution to this system of equations satisfying this initial condition. It is easy to check the solution by evaluating the left-hand side or right-hand side and comparing these two functions as a function of t. And it is easy to check the initial condition. If we substitute 0 for t, we have 4 plus 3 is indeed 7, and 2 minus 6 is indeed 4. So this is how to solve the system of equations. Two more problems may appear. First, if this equation has no real roots, only complex roots, we will see this. And another complication might be if lambda 1 is lambda 2, if lambda 1 is equal to lambda 2, but we will not consider this case.